Hello everyone, I'm Rittig from RWTH Aachen University. In this video I will present our recently published graph neural network tool for the prediction of physical-chemical properties of molecules. I will show you a tutorial on how to use our tool and how you can build your own model. The general structure of our graph neural network tool is shown on this slide. So we take molecular smile strings as an input and then transform these smile strings to molecular graphs. Then the molecular graphs are fed into our graph neural network, where graph convolutions and pooling functions are applied to get the molecular fingerprint. And then this molecular fingerprint vector is mapped to the property of interest by deep learning. And with this tool you can predict any property of interest. We recently used our GNN tool for the prediction of fuel ignition qualities of oxygenated hydrocarbons. Therefore, we predicted the DCN, the MON and the RON, so the derived octane number, the motor octane number and the research octane number, which are important key figures in the design of future biofuels. For example, the octane numbers are shown here on the pumps at gas stations in the picture on the right. And if you are interested in more details of our method, please refer to the video which you can access under this link here on the right hand side. The main outcomes of our work were that the GNN tool offers an end-to-end learning of molecular properties without complex descriptors. We can overcome limited data availability by multitask and ensemble learning. And we also published an online tool which you can access under this link here. And at the website, you can type in a molecular smile string into the field here and then press calculate. And then the GNN tool will predict the DCN, MON and RON. And the website will show you the prediction of the GNN. Our method is described in detail in a recently published paper in Energy and Fuels. And we also provide the code and data open source at a GitLab repository, which you can find under this link shown here. So in this video, I would like to show you a step-by-step tutorial on how to use our tool. And we will start with the installation, then I will show you how you can use the tool. And at the end, I would like to show you how you can build your own model with your own data. So let's start with the installation. For using our tool, the packages shown on this slide are required. So we need RDKit, we need PyTorch Geometric, we need the k-GNN tool, and at the end we need to install our GNN tool for fuel ignition quality. And with that tool you can also predict properties of your interest, so other properties than fuel ignition quality. So in the next step I will go to the screen sharing mode to show you how you can install all these required packages. Okay, so now you can see my screen. We are in a Linux system and will install the required packages within a Conda environment. So to create a new Conda environment, I will just add the Conda path to my system and then create a new environment with the name GNN FPP for fuel property prediction, and I will use Python with a version of 3.7. When the Conda environment is created, we can proceed, and we will also need a C++ compiler. So I will load the pre-installed GCC with the version 6. And when this module is loaded, we can now install the required packages within our environment. So we next activate our Conda environment and can now start with the installation. So for RDKit, we will use the statement conda install -c conda -forge RDKit, and now RDKit will be installed. This can take a while. So when RDKit is installed, we will next install PyTorch. Therefore, we will go to the PyTorch website and click on Get Started. Then we have to select our system parameters. So in our case, we have Linux, Conda, Python, and as my computer does not allow for GPU acceleration, I will install PyTorch without CUDA. But if you have a graphic board that allows for CUDA installation, you can also use PyTorch with CUDA. But in our case, we will use CPU only. Copy the command line and insert it here. And now the PyTorch installation will run. So when PyTorch is installed, we can install PyTorch Geometric, and therefore we will go to the website of PyTorch Geometric, click on installation, and first check the torch version we have installed on our system. You can just copy the link, the command line here. So in my case, this is the torch version 1.4. And also if you have installed CUDA, you can check your CUDA version here and next install the torch packages from source. Therefore you can click on our wheels, select the torch version, and then you have to find the system parameters here. So for torch cluster, for example, you go to torch cluster, the latest version. In my case, it's Python 3.7 and the Linux system. Then I copy the link and type pip install, insert the link, and then torch cluster will be installed. And this we will do for all the other torch packages. So not only torch cluster, but also if we go back for torch sparse, torch scatter, torch spline conf, and torch geometric. And after that, we can then install the next packages. Now that we have installed all torch extensions of PyTorch Geometric, we can install the k-GNN package. We go again to the web browser and to the repository of the k-GNN package. Then we go to code and copy the link. Go back and type pip install git plus the link, and then the k-GNN package will be installed. As a last step, we will download the GNN tool for prediction of fuel ignition quality. Therefore, we will go to the link I showed you in the presentation. Then click at the download button and click zip file and store the file at a defined place. Then we can unzip the file, and when this is done, we can add the Python path of the unzipped files to our shell. Now we can go to the path of the GNN tool. So and when we direct it to the correct path, we can now type ls and see the directories within our package. And just to show you that we can now use the tool, we go to trend model and can now type in or execute the Python code for the prediction of a single molecule, for example for CC. And now we should get some predictions for this given molecule. This can take a few seconds. And here we see the predictions. Now that we have installed all the required packages and the tool, I would like to show you how you can use our tool, and therefore we will go back to the screen sharing mode. Okay, back to my screen. Let's go into the GNN tool folder. We can see that we have different directories within this folder. We have a data folder, we have dependencies and docs, we have a smiles to molecular graphs folder, we have sources, the trained model, and also the training script. So let's go first into the data folder. Here we have the different data sets for the DCN1 and 1 that we use in a single task training. And we also have the joint data set that we use for our final multitask model. So if we go into the joint data set, we can see that we have here training data and test data. And all the data sets are stored in the raw folders as a CSV file, and within the CSV file we can see the different molecular compounds, the corresponding SMILE strings, and also the assigned property values. So here the DCNs, the MONs, and the RONs. So going back to the overview, we can also see that we have a smiles to molecular graphs folder. Within this folder, here's the code stored where we transfer the SMILE strings to molecular graphs. So for example, here we can see the corresponding atoms that are transferred to nodes. So in our case, HCO atoms. And if we go down, we can also see the bond information that is transferred right here. And this is a fully automated pre-processing step, so we just provide the SMILE strings and then the SMILE strings are transferred to molecular graphs. Another folder is the trained model folder that we have already seen in the previous screen sharing mode. Here are the model parameters stored of our final model, and here you can also find the Python codes that you can use to make predictions. And the last folder is the training script folder. Here we have the different model architectures stored and the corresponding training scripts. So for example, if we go to single task training, we can see the Python code for running a single task model training, and we can do this right now. So we just create a new folder that we call training, and then we go back to the shell. We are still in our Conda environment and are within the GNN tool folder. Then redirect to training script and to single task learning. And now we can run the training script for a single task model. And we can also provide the target to the DCN. And then we run our training. And if you operate on a GPU, the training will be much faster, but also for the small data sets we look at, the training will be reasonable fast. So here you can see the epochs of the training and the validation mean absolute error that is decreasing during the training, as well as the training error and the loss. So when the training is finished, the final model will be stored in the training folder we just created. And here we see the property we predicted, and the model is stored here. We can also see the training, validation and test error decreasing during the epochs. And so you can try to retrain our models or to add new data for DCN-mons and RONs and train your own model. In a last step, I would like to show you how you can build your own model. That means how you can use your data and our GNN tool to build your own property prediction model. Therefore, we will go again to the screen sharing mode. So let's assume you have your own dataset with your properties. Then you first split your dataset into a training and test dataset, and you create two new folders, a training folder and a test folder. Then you take the dataset and put it into the corresponding folders. So the test dataset in the test folder and the training dataset in the train folder. Then in both folders you create a new folder called raw, and then copy the dataset, insert it into the raw folder, and also rename the dataset to raw so that our GNN model recognizes the dataset. And we do the same for the test set. We also call this file raw. And after that, we create a new folder called default so that we have the same data structure as in our DCN-mon and RON datasets. Then we put the training and test folder into the default file and create a new folder with the name of the property. I will just call it, for the sake of simplicity, property. And then we go back into our GNN tool in the data folder and copy this property folder into the data folder. Then we can train a new GNN model on the property data, and therefore we will go back to the shell and use the training script for our single task model in this case. So we can just go to the training script folder, and in our case to the single task training. And then we can run the training script with the command line Python training single task model, and we define our target property. So in our case we called it simply property, but you can name it whatever you want. And now the training will be initiated. Here you can see that the pre-processing starts, so the smile strings are converted into molecular graphs. And it is important that for your new dataset you use the same structure as we do for our DCN-mon and RON dataset. So here we go to the dataset, for example the training set, and we can see that we have first the molecular compound, the name, then the smile string, and then the corresponding label in the third column, so that our model recognizes the right columns within the CSV file. And it is also important to note that if you use molecules with other atoms than hydrogen, carbon or oxygen, then you have to modify the transforming of smile strings to molecular graphs. Therefore you go to smiles to molecular graphs folder and go into the reading single task in our case, and then go to the atoms, and here you can see H, C and O, and there you can then add the other atoms you consider in your molecules. And it is also important that you then modify the training script. So we go to training script, single task training, and as we use higher order GNNs, we have to change the pre-processing. So if we use more than 3 types of atoms, we have to change it here, the number to 4, for example. And now the model can also be trained on molecules with more than 3 types of atoms. So the training is still running, and the model parameters are stored in the same training folder as I showed you in the previous step. So we can go to single task training, and then we can see for our property, which we called here property, the model parameters are stored in this folder. And we can use these parameters then for predicting the properties of other molecules that were not included into our training set. And with that, I would like to thank you for your attention, and please feel free to use our GNN tool. We are happy to connect via LinkedIn or YouTube, where you can also find other videos of us. So thanks again.